All right, it's 11:15. I think we'll get started. So welcome to the last class of the semester. Just as a reminder, the final is comprehensive, and we've covered a few of these topics, right? We've covered smart materials, we've covered conducting polymers, we've covered 3D printing. We haven't covered biomaterials, so there won't be any biomaterials questions on the final, but there's probably going to be 2 or 3 or maybe 4 questions on these other topics. So don't forget about those in addition to your regular review. And of course, the final review slides we have are right here. So make sure that you can access all of the PowerPoints, all of the things that you need to review for final. If you can't, let me know beforehand. So any questions or any comments? Yes. Yes, you need to do all the PLAs. It will just be good for you. Yeah. You need to do the PLAs. So you have 2 PLAs due today and a homework, because I know that there's nothing else going on today. So you should have plenty of time to do that. Any other questions? All right. Don't forget about office hours, since the final is open Wednesday, Thursday, and Friday. These are the scheduled office hours today, Monday, and Tuesday. But email me if you have a question. You're welcome to make an appointment, but when you make an appointment with me, you need to say, I want to meet on this day and this time, or give me a couple options. Don't say, do you want to meet anytime? Because I might pick a time that's not good for you, but since you have finals and everything else, give me a couple of options if you want to meet for office hours, and then we'll make something happen. But there won't be any questions answered about anything on Wednesday, Thursday, Friday of finals week, unless there's a massive problem. There's a real issue with the exam. You never know, Canvas, right? Or, something else goes wrong. I won't do any correspondence on Wednesday, Thursday, or Friday. You're welcome to email me on Saturday or Sunday after the exam period. It's going to take me probably till like Monday or Tuesday to get the grades in. So don't email me on Friday afternoon saying, where's my grade? I won't have it yet. All right. So here's the final. It's the usual procedure. And importantly, there's going to be about 30 or 40 multiple choice questions. I think I have 36 right now, but you'll have 2 hours on Canvas to do that. So you'll have 120 minutes to answer those questions. It's longer than a regular exam, but the final period is longer than a regular class period. And you'll have written questions that are worth about 8 to 10 points. Like 4 written questions, something like that. So we haven't had any real issues with uploading the written questions or anything like that. So I assume that that's going to go fine. Yes. Remember, written questions should be turned in a reasonable amount of time after the multiple choice. So like 40 minutes, 30 minutes, 50 minutes, but not 4 hours, not 6 hours, reasonable. There is no time limit for the written, but I've taken the exam. I know how fast I can write, even if I have to think for a few minutes. It shouldn't be many hours later. It should be a reasonable amount of time after. Yeah. Any other questions? Okay, I assume the final is going to go great. Everyone has actually done a really good job getting their stuff in on the other exam. So as long as Canvas doesn't do something horrible to us, we should be good to go for the final. And if you mess something up with turning in the written part, it's okay to turn it in again. I mean, it's okay to put it in the comments or send it to me by Canvas email. That's fine. But a really nice way to make sure that you've turned in the right part for the written versus the scratch paper is go back and look at the file 5 minutes later and say, oh, is the file that I thought was in there? Because sometimes there's a page missing. Sometimes Cam Scanner gives me a black page for whatever reason. And so it will prevent me from emailing you the weekend after final saying, please turn it in or please get me this file. So just double check that your written part is uploaded and complete and everything's good. Go back in 10 minutes later and just check it. All right, and if you want to send me an email or send it to me by email, if you're unsure, send it to me by Canvas email, not regular email. Any questions? All right, so you can read those other slides, but basically we have covered a lot of ground in polymer science, especially if you remember all the way back to exam 1, thinking in exam 2, thinking about how you make polymers, what are some of the key features of polymers. You can be guaranteed I'm going to ask you 8, 10 questions, maybe more on this type of stuff. So you want to go all the way back and think about how to make polymers, step growth, chain growth, Carruthers equation, molecular weight, things like that. So in terms of talking about polymers, remember that we covered a lot of things that are statistical copolymers. So if I can draw on here, statistical copolymers. Of course, we covered a lot of things in homopolymers, alternating copolymers. When we talked about these types of copolymers, what was the concept that we used in order to make copolymers and figure out what their composition was? What sort of tied it all together? How do I know that styrene reacts versus methyl methacrylate reacts? What was the concept? Reactivity ratios, right? And so, you know, remember that funny graph I'll show you again today where we were above the 45-degree line, below the 45-degree line. You can be guaranteed, or if we made block E type, block E copolymers, depending on the reactivity ratios of our two monomers, we learned a lot about how these polymers go together. We also learned about M0 copolymer. So if you remember all the way back to exam 1, and there's a question on exam 1 practice, how to calculate M0 of a copolymer given the molar ratios of the two different monomers, you need to remember that as well. So there's a lot embedded in the copolymer part. We didn't talk too much about block or diblock copolymers or graph copolymers. And so let me just, whoop, not much on those. So this is usually called a diblock because it's got one block here and one block here, but those are harder to make. We didn't talk a lot about block copolymers, but we did talk about blocky type copolymers based on the reactivity ratios. All right, so don't forget about linear polymers, branch polymers, and of course crosslinks. What is another name for crosslink network polymer? What do we call that? Thermoset. You can't deform it under heat. And you know that both linear and branch polymers are thermoplastics. Good. And of course, branching can decrease crystallinity because the branch doesn't fit in the crystal. So how do we get branching in polymers? What are two of the ways that we know how to get branch polymers that we studied in detail? What about short branches? How do we get short chain branches in our polymers? Yes.
Backbiting.
Backbiting or chain transfer to polymer, or sorry, intramolecular chain transfer to polymer, right? When the active chain end comes and reacts back on itself, and then you get a short chain branch. How do we get a long chain branch? Yes. So you can get multifunctionality, you can have multiple DFs, but what's another way? Say if you're just making a linear polymer, and what type of process leads to long chain branching? Yes.
Two polymers, or like one polymer reacts with the side of
That's right. So between two polymers is intermolecular chain transfer to polymer. So does short chain branching or long chain branching influence the molecular weight of the polymer when we have chain transfer? No. What decreases the molecular weight of a polymer when we have chain transfer? Chain transfer to what? Chain transfer to monomer, chain transfer to solvent, chain transfer to initiator. And so we can look at what type of chain transfer we have, and we can say, okay, this won't change the degree of polymerization, or this will. So don't forget about all that chain transfer stuff that we studied. All right. This is a really important equation, so make sure you don't forget it. And you really need to know whether you're dealing with the degree of polymerization or you're dealing with the molar mass. And so there will be some times that I give you, 10,000 grams per mole, right? That's the molar mass of the chain. And you might be using the Carruthers equation to figure out what the degree of polymerization is. And of course, those are connected by M0, which is the molar mass of the repeat unit. So that's basic, but there's a couple of details with figuring out what M0 is, especially if you have some sort of copolymer that looks like this. And so we had questions on that, and that's on the practice exam. How do we figure out M0 for a step growth polymer? First of all, what's an example of a step growth polymer? Nope, that's chain growth. Chain reaction, free radicals. What's an example of a step growth polymer? Yes.
condensation.
A condensation reaction. Give me a example, like a polymer name that's a step growth polymer. Polyester or PET, polyethylene terephthalate. That's a polyester. How do we figure out what the M0 is of PET? How many monomers are in the repeat unit of PET? 2. And so you figure out M0 by what? Not the mole fraction, because it's 1-to-1, right? You have alternating terephthalochloride and ethylene glycol. Yes.
You add the two monomers, subtract like their molecular weight, subtract whatever condensates out, and then divide by 2.
That's right. So you have to divide the repeat unit molecular weight by 2 to get M0 for step growth copolymers. If you don't know what I'm talking about, you need to go look that up, because that goes into the Carruthers equation in order to make sure you get the right degree of polymerization. So I'll just insert a slide here. I don't know if I have a slide on it. For step growth copolymers, we usually have 2 monomers in the repeat unit. So if we're making nylon 6,6, right? Or if we're making PET, or if we're making some other type of step growth copolymer, we've got 2 monomers in the repeat unit. So M0 equals repeat unit molecular weight divided by 2. And this is important to get XN for Carruthers equation. And we've had examples of that before. We've done clicker questions on that, but that's the one key difference for polystyrene. What type of polymer is polystyrene? Is it chain growth or step growth? Chain growth. Is polystyrene a glassy polymer or a rubbery polymer? Glassy. It's got a high TG. But the M0 of polystyrene is just this. There's one monomer in the repeat unit. And so we could just get M0 by adding up all the atoms. For PET or other types of step growth polymers, we have to remember this in order to get the right degree of polymerization. All right. Any questions or comments on that? All right. Remember, molecular weight or molar mass is a distribution, and we can characterize the distribution by a number of parameters, Mn and Mw. How do we calculate dispersity? That's right, Mw over Mn. What's the minimum dispersity that we could ever have for a polymer? 1. So D has to be greater than or equal to 1, which means what? What always has to be true if dispersity is always equal to 1 or greater than 1? Mw is always greater than or equal to Mn. That's right. Yeah. And so we have some ways to calculate Mn and Mw. And of course, we can calculate number average degree of polymerization. And if we know the weight average molecular weight and M0, we can get the weight average degree of polymerization. But don't forget about some of the easy stuff. Like if I give you dispersity and Mn, you can calculate Mw right from there. And so there are some slides on how you calculate Mn and Mw based on the number of moles or the mass of each sample you might have. And usually those samples are monodisperse. So what does monodisperse mean? If I tell you I have a 10,000 gram per mole sample of polystyrene and it's monodispersed, what does that mean? That's right. Every single chain is 10,000 grams per mole. So the dispersity is 1. I mean, that's why it's called monodispersed. 1 dispersity. But that's how a lot of those questions go. If I have 2 monodispersed samples, say I have a 10,000 gram per mole monodispersed sample and a 30,000 gram per mole monodispersed sample, and I mix them, what's the resulting Mn and Mw? So make sure you know how to do some of those problems. Any questions on molecular weight, M0, things like that? All right. So remember the type of polymerizations that we talked about. We have a BA, well, this is a BA polymerization. BA. We also have our ARB polymerizations for step growth, and we can have AA polymerizations, that type of condensation reaction. But the key is that we need a DF of 2 or greater in order to form a polymer in the first place. And so we looked at some monomers and we said, well, can you make a polymer out of this? And you have to look at the degree of functionalization. And of course, anything with the DF greater than 2 gives branching and networks. So the DF has to be exactly 2 if we're going to make linear polymers. And if the DF is less than 2, no polymer. And so make sure you're able to identify different types of monomers. Make sure you're able to identify different types of monomers that go into all these different types of polymers. We don't have to worry about polysulfides, but polyether, polyester, polycarbonate, polyamide, polyurethane, and polyurea. Those are all linkages, and you should know what the monomers are for those linkages. All right. And the other thing that you should know is generally what's step growth, what's chain growth, what's going on with those 2 types of polymerizations. And here's the slide on the different types of polymerizations. And so give me an example of an RA2 polymerization. What's a good example of that? What type of polymer do we make and what type of monomers might we use? Polyether is a good one. And so what type of monomers do we use to make polyethers? Diols. So we could take something like 1, 2, 3, 4 butane diol, and we can condense it with another butane diol. 2, 3. And since it's a condensation polymer, we're going to get rid of water and we form our ether bond. So that's an important process. We've talked a lot about AABB and even about ARB, because you can see the two different functional groups in that case, but don't forget about polyether condensation of two diols. Any questions or comments on that? All right. There's no clicker questions. I'm done updating the clickers. But you should be able to answer. I mean, this should be a 10-second question on the exam. Okay, I'm looking. Let's see. This really looks like a polyester, but I know this oxygen is over here. And so even though it's a little tricky, it's not a trick question. It's, are you paying attention? And so this is a polycarbonate, because I know that this is a carbonate linkage, but I really need to remember that we can slide those parentheses back and forth. So it's really important for you to look at those slides in that first section and recognize how to put polymer formulas or polymer chemical structures together. And there's some tricky questions, right? One carbon is out of place, or there's an extra methyl group, or something is missing. And so you really have to do your accounting very carefully in order to make sure that you have the right answer, and check it. There should be plenty of time on the final to make sure you have the right answer. Okay, so Carruthers is really important. And so we have degree of polymerization related to molecular weight. And so the things that we looked at in Carruthers are, we can get the degree of polymerization knowing the extent of reaction and the stoichiometry. And I was looking at practice exam 1 earlier this week, and there's some good questions on practice exam 1 to warm you up to this. And so you don't just have to go back and stare at the notes. My suggestion is go back and look at all the practice exams. That's a really good way to start your study. And what this equation tells us, when R is 1, what does this equation reduce to? First of all, when R equals 1, what situation are we under? Equal numbers of A reactants and B reactants. So we apply Carruthers to this situation right here. And so if R equals 1, we have equal moles of A and B functional groups. And so if we just substitute in R equals 1 into this equation, what does this reduce down to? X bar N is 1 over 1 minus P. Great. Make that a little neater. So what does this tell us? If we want to get high molecular weight, X bar N should be a high number, right? And so how does this equation tell us to get high X bar N? A high extent of reaction. So we need a P that's pretty close to 1. So P is between 0 and 1. And so of course, when P is 1, X bar N is infinite, so we never get there all the way, but P has to be 99.3, 99.8, 98%, or 0.98 in order to get high X bar N. So that's important. Okay, and here's the question. So these questions will go something like this. We want a polymer with this molecular weight. At what extent of reaction should you stop your reaction to obtain this size polymer? So you know extent of reaction is P, And so we need to find an equation with P in it. Turns out for this, R equals 1, right? Because we had the same number of functional groups that react with each other, because this is going to be a polyether. And so what do we need to figure out in order to apply one of these equations or the Carruthers equation? What do we need? What do we need to know? We just can't put 10,000 equals 1 over 1 minus P, because that's not what X bar N is. So how do we figure out X bar N? Yep, X bar N equals 10,000 divided by the repeat unit molecular weight. And so if we, so if we go here, we know that the M0, remember there's only one monomer in the repeat unit. Let me put M0 here just to make sure that, whoops. M0. So there's only one monomer in the repeat unit, so we could just add this all up. This is 72 grams per mole. And so we get an X bar N of 138.9. And so decimal places are going to matter here. Usually we have extensive reaction with 3 decimal places. That's probably good enough. And so when we solve this equation for P, we get an extent of reaction of 99.3%, which is what we need to get 10,000 grams per mole polyether. So this should take you 5-7 minutes. That's fine. If this is taking you 20 minutes on the final, that's a little bit too long. And so you should be able to sort of gauge your progress on the final by, is the question complicated? Do I have to calculate some stuff? How long is it going to take me versus something like this question that I can just solve by inspection, and that should be a little bit faster. Any questions on this? Yes.
Can you explain the R again?
Yeah. So remember, R is the ratio. I don't have it on here. Where is it? R is the moles or the number of A functional groups versus the number of B functional groups. So the problems are often something like 1.0 moles of diol plus 0.9 moles of diacid. What do we make with a diol and a diacid if we have those two monomers? What type of polymer do we make? Polyester, right? And so RA or R equals, it's the minority functional group. So it's 1.8 over 2.0. Because remember, there's 2 functional groups if I say it's a diol or a diacid. And so if I have equal stoichiometry, R is 1, but this offset stoichiometry I have to account for in Carruthers. Any questions? Yeah.
Like 2 over 1.8.
No, that's not the definition of R. Remember, R is always minority functional group in numerator. And remember the definition of P, it's not based on monomers, it's based on the number of functional groups. And so again, when I was looking at exam 1, there's a question on this, so it's useful to go back and review how to get that. Yeah, so remember what the definition of R is, and remember what the definition of P is. Questions or comments? All right. And then we have some statistical Carruthers. So usually we talked about weight fraction or the probability of finding a certain length of polymer. So if it's trimer, X is 3, it's a monomer, X is 1. So you can take a look at that. There might be one question on this. All right. Chain growth. Remember the key features of chain growth. There's a lot of things in there, but what were the two types of termination that we talked about? How can chain growth polymers terminate? Combination and disproportionation. So remember the key features of that. We had an exam question on counting the number of molecules. So remember, in combination, you have 2 active chain ends that come together and form 1 molecule. So termination looks like polymer chain plus another polymer chain. And so you start off with 2 moles of molecules, and in combination, you of course only have 1 mole. And in disproportionation, you get a double bond on 1 molecule, but you start with 2 molecules and get 2 molecules. So remember that counting problem we did, and that's related to what variable tells us the mixture of combination and termination that we might encounter? Q. So make sure you look up the definition of Q. It will be on your equation sheet, and there's an equation sheet already posted on the practice final. So make sure you're familiar with that. And so getting the right Q or having information about Q or knowing about the number of molecules tells you about what type of termination you might have. What type of compounds are good free radical initiators? Peroxides, azo compounds. Great. What other types of chain growth? What other types of chain growth polymerizations did we study besides free radical? Cationic, anionic. Which type of chain growth polymerization doesn't have well-defined termination step? Anionic, that's right. And living. So we studied living polymerization. And what's the special feature of living polymerization? We look at molecular weight or X bar N. Either one is fine. As a function of conversion, what defines a living polymerization? Constant slope or a straight line. So this is living. And you can figure out from this chain growth. And this is step. Great. And we talked a little bit about the type of electron transfer initiator you need for living polymerization. That's getting into the details, but knowing living anionic. Now there are living free radical polymerizations, which you'll study later. There's living cationic polymerization that we didn't talk about, but living anionic polymerization is the one to remember. Any questions on that? All right. What is the head carbon of this monomer? First of all, what is the type of polymerization that this monomer undergoes? Chain. Could be free radical, but in general, this does chain. Which one's the head? B. So this looks tempting. You know, I see a carboxylic acid there, but if I wanted to make a polyester out of this monomer, what's the degree of functionality for a polyester? 1. There's only 1 carboxylic acid. What's the degree of functionality for a chain growth polymerization? 2. So this is a pretty useless monomer if I wanted to make a polyester, right? Because the DF is not high enough. Great. Why do we care about head and tails of monomers? When did we cover that? We talked about how free radical polymers are built up, right? And about the chain microstructure. And one of the really interesting things is that the active center resides on the head, which is most stabilized because it's the most substituted carbon. Why else does the active center reside on the head? Or why do we usually have head to tail connections? That's a good answer. So when we have an active chain center with a radical on it, if we have something like styrene, first of all, this is a more stable position for the radical to reside. And it's a lot easier for this radical to attack the tail of the styrene monomer versus the head of the styrene monomer. And so what type of termination is shown here? Combination, taking two active chains and making one. What type of linkage is this right here? Head to head, because the head of one styrene or the head of one substituted monomer is reacting with the head of the other. So make sure you can identify head to tail, tail to tail, head to head, etc., and make sure that you know in general when you take one of these polymers or take one of these monomers, how to make a polymer out of it and get the right functional groups in the right places, and how to recognize a vinyl-based monomer or chain growth monomer in the first place, right? If I asked you, what polymer can you make out of this monomer, you say, okay, well, I've got this double bond. All right, so let's see. I'm just going to turn it around because I know that a lot of my chain growth polymers have a backbone that looks like that, and I just need to get the carbonyl in the right place. OH. So I've got 1, 2 carbons in the backbone because I'm gonna do 1 carbon that way, 1 carbon that way. So I've got 1, 2 carbons there. That's good. And then I've got 1 connection to the carbon right here for the carbonyl and 1 connection to the OH group. And so this is the polymer structure. And I guarantee you, I'm going to ask you 2 or 3 questions. Here's the monomers. What are the polymer? Here's the polymers. What are the monomers? And so you're going to have to know a few things about that chemistry perspective. Any questions or comments? All right, hopefully this is just refreshing your memory. All right, so based on this, do you think this monomer undergoes anionic or cationic polymerization? Cationic, I have 1 vote for cationic. Why? So what does, yeah, so the CN is what type of group? So this is electron withdrawing. So what do electron withdrawing groups prefer to do? Stabilize what? They stabilize negative charges. So based on that, nitrile group stabilizing a negative charge, what type of polymerization do you think this monomer prefers to undergo? Anionic. So the anion is stabilized. So it's important to remember that anionic polymerization is named for the growing chain end. Cationic is the same way. And so depending on the functional groups that you have on the head group, you can figure out what is the preferred pathway for polymerization of these monomers. Let's see, what's this question? Increased chain transfer to monomer. If you remember back 30 minutes ago when we were talking about this, what's the best answer? Decreased degree of polymerization. Perfect. And the way that you figure that out is that you're transferring a polymer active chain end to a small molecule, something that has a lower molecular weight, right? So you're backing up the degree of polymerization, or you're decreasing the overall degree of polymerization. If you chain transfer to polymer, no change in X bar n. Because one polymer is growing versus another polymer is growing, and in the overall distribution, that doesn't matter. So that's a really easy way to think about a question like this. I'm transferring to a small molecule, so X bar n has to go down. All right, tacticity. So what is, when I say a polymer has tacticity, what does that mean? What are we trying to evaluate? Chiral centers and how those chiral centers are distributed along the polymer. So remember that polymers in this class are only 100% isotactic or only 100% syndiotactic. If there's no pattern, they're atactic. Or if the polymer is not able to have any tacticity, there's going to be no tacticity, or it's undefined. And so what do we need in order to have a monomer that has the potential for tacticity in a polymer? We have to have stereocenters, or we have to have 4 different bonds to carbon. So a monomer like this is symmetric we have one functional group there. We've got the same one here. And then of course the chain ends are 2, 3. And so we only have 3 different functional groups. On carbon. So no stereo center. Whereas if we have something like this, we've got a hydrogen right here. So we have H, we have a methyl group. Let me just draw on the methyl groups here. And then we have the 2 chain ends. Remember, the polymer going one way is one functional group. The polymer going the other way is the other functional group. And so now we have 1, 2, 3, 4 different functional groups on this carbon right here. So we can have a chiral carbon. Because remember, back to organic chemistry, you need 4 different substituents in order to make that carbon chiral. Okay. And so we, I don't have any slides on that, but we do have some tricks for evaluating the tacticity just by inspection. Remember, we can rotate those functional groups to get them all aligned on the same side of the chain. So that's worth 10 or 15 minutes of review before the final. Don't forget about dienes. What's the DF of a diene? 2. DF equals 2. There's only 2 connections to other polymers. Remember, if you need to be conjugated equals diene. If we have some sort of monomer like this is not a diene, or it's not a conjugated. DF equals 4, so this will lead to branching and cross-linking. And dienes are tricky because there's all these different additions, right? There's 1, 2, there's 3, 4 when we have this functional group here. There's cis 1, 4, there's trans 1, 4, and so these, all of these different connections you should know and be able to draw out for whatever diene you're interested in. Butadiene, of course, this 1, 2, 3, there we go. No 3, 4 connection. Always 1, 2. It's 1, 2 if you connect it on one side. It's 1, 2 if you connect it on the other side, because it's a symmetric monomer. But remember, we number dienes with the functional group having the lowest number. So where the functional group is always where the 2 position is going to be, and 1 is right next door. So make sure you know how to number dienes. Questions on that? All right, what other goodies do we have here? Make sure you look at these slides. So we can talk through reactivity ratios. I want to mention 1 or 2 more things, but make sure that you can solve problems like this, where I give you reactivity ratios and you tell me about what copolymer is made, or you tell me about which active center reacts with what active center. So is methyl methacrylate more or less reactive with diphenyl acetylene than diphenyl acetylene? So that's a really confusing question, right? And so what pair of data do we have to look at? What line are we looking at when we talk about the reaction of methyl methacrylate with diphenyl acetylene? 3. So what does RA tell us? The reactivity of go ahead, say it. With what? So it's, yeah, so the definition of RA is what? So remember, it's homopropagation over hetero. So it's KAA over KAB, right? So a reactivity ratio of 0.21 tells us what? Diphenyl acetylene prefers to react with methyl acrylate. And same thing here, the reactivity ratio of RB of 50 tells us what? Methyl methacrylate prefers to react with what? Itself, methyl methacrylate compared to diphenyl acetylene. So if you pick apart these questions, you can figure out exactly what's going on. But this is a tricky question. This is a tricky question. I'm only going to ask a couple reactivity ratio questions, but you need to be ready for those. And be ready to talk about this plot as well. All right. We have some mixing. We have some characterization. We've done that recently, but we are out of time for the semester, but we're not out of time for office hours. And so please come to office hours, do the practice exams, and Good luck with your finals. Thank you very much.